So what are we going to be talking about is solutions and solute and solvents, concentration, and then polar and nonpolar molecules in solutions. Solution. In a solution, one solvent is the solute, and the solute is dissolved in the solvent. Solutions can be liquid, gas, or solid. Bronze is an example of a solid solution of copper and tin. Solid solutions are also known as alloys. A mixture that has the same composition, color, density, and even taste throughout is called a homogeneous mixture, or homogeneous, but homogeneous is probably the better way to phrase it. The solute is the substance being dissolved. It may be a gas, a liquid, or solid, just like the solution can be a gas, liquid, or solid. And again, remember, a solution is made out of a solute and a solvent. So what's a solvent? A solvent is the substance doing the dissolving. The solvent is considered to be the component of the solution which is present in larger amounts by weight. So if you have a solution of a gas within a gas, the solvent would be the one that's greater than 50%. The solute would be the gas that is less than 50%. And again, the solvent may be liquid, gas, or solid. So for an example of a gas that is a solution, you can consider atmospheric gas. The solute would be the 20% oxygen, and the solvent would be the 80% nitrogen. A gas, as you remember, expands to fill whatever size container that it's in. So the solution would be the atmospheric, where it's completely mixed. You have a homogeneous mixture there of oxygen, 20% oxygen, and 80% nitrogen. Solute particles affect physical properties of the solvent. So you have antifreeze. Antifreeze you put in your radiator to cool down the engine, but it doesn't do you much good if it freezes at 0 degrees and you're up in Alaska where it gets down to 20 degrees easily, or here in the boiling point where it gets very, very hot. You do not want it to boil away like water would. They start with water, but then they add extra elements, extra solutes that change the freezing point, which is when it starts to crystallize. So you interfere with that crystallization. And then you have another type of antifreeze that you might use for the summer that interferes with the boiling. It stops the evaporation. Now let's talk about solubility and concentration. Solubility is the maximum amount of a solute that can be dissolved in a given amount of solvent at a given temperature. Keywords here are given temperature. Is that temperature? It's very temperature dependent. Solubility in chemistry is different than solubility used in like cooking. Solubility in cooking is just how much stuff you add to it. Well, that's not the case. It means specifically the maximum amount that can be dissolved without it falling to the bottom. Concentration, solubility, and common usage are approximately the same. You know, solubility is how much you can put into it. Concentration is how much you can put into it. But in chemistry, that's not the case. Solubility is the maximum amount you can put into it. Concentration is how much is in there, dissolved in the whole solution. You can put it as a percentage, or you can present it as a mass per volume. In this curve here, so concentration on this curve, you can see is right there. It's the percentage of the carbon dioxide in the atmosphere. And here's the year. So you can see where the concentration has been going up every year since the 1700s. Then all of a sudden when we started burning fossil fuels, it took a huge leap, and it's continuing to this day. So that's the concentration. That's how much is in the atmosphere for this particular curve. Rate at which substances dissolve can increase depending on many factors. So in other words, how fast you can dissolve salt in water depends on many factors. Stirring. When you add sugar to your drink, don't you stir it to increase the rate at which it dissolves in there? What's another thing you might do? Increasing the surface area. If you're trying to saute onions, would you stick the whole onion in the pan? Or do you chop it up so it cooks at a quicker rate? What you're doing is increasing the surface area. And then you might turn the temperature up. Most substances, you give it more energy, it's going to dissolve faster. Not true for all substances. There are three types of solutions. You can have an unsaturated solution, which means it can hold more solute at its current temperature. Let's say you've got tea, hot tea, and you may add just a tiny bit of sugar. It can hold a lot more sugar, so it would be an unsaturated solution. A saturated solution is one that contains all the solute that it can hold at that temperature. So you have that same cup of tea. You keep adding another teaspoon of sugar, another teaspoon of sugar, and eventually it won't dissolve. Eventually any more sugar that you add will just settle to the bottom. That would be a saturated solution. And then you have a supersaturated. It's a little bit difficult to obtain a supersaturated solution. That's where you have the solubility curve that says that at, let's say, 20 degrees, it can hold 2 teaspoons worth of sugar. But somehow or other, you got it to hold 3 teaspoons worth of sugar. There's ways you can do that. It's very unstable though, and if you touch it, it may easily crystallize out. How do we know if something is going to dissolve? We use the phrase like dissolves like, and that's when we're talking about polar and nonpolar compounds, which go to this site. It really is an awesome site that's going to show you the YouTube video of how different substances dissolve different things differently. You've got 6 solvents and they put in 2 solutes, and it's just amazing. I wouldn't have believed it unless I saw it for myself. So like dissolves like is an expression used by chemists to remember how some solvents work. It refers to the polar and nonpolar solutes. So basic examples: water is polar. Salt, NaCl, is ionic, which is considered extremely polar. Like dissolves like, that means that polar dissolves polar, so water dissolves salt. Nearly all compounds fall into these two categories. One, water-loving. One is water-hating. Oil and anything that will mix with oil are considered to be hydrophobic, water-hating. They just don't mix. And you know that. You know water and oil separate just as soon as they mix. You have to keep shaking up your salad oil so that you're not just getting the oil that floats to the top. So get a chance and stop and pause and go ahead and look at that video. It really is pretty good. Water is considered to be a universal solvent because a lot of things dissolve in it. Water is slightly polar, so anything polar is going to dissolve in water. It forms hydrogen bonds. We haven't talked about hydrogen bonds much, but hydrogen is a mild bond. It's not as strong as covalent nor ionic, but it is a bond that forms due to the attraction of negative and positive. So anything that is water-loving dissolves in water, like salts, sugars, acids, alkalines, that's another word for bases, and some gases, carbon dioxide and oxygen, dissolve slightly in water also, which we know because fish like the oxygen in the water. However, water does not dissolve things that are hydrophobic, water-fearing substances, such as fats and oils, as we just mentioned. How well do you remember your polar and nonpolar molecules? Well, let's go ahead and look at that. Molecules with slight opposite charges on either side are polar molecules. In other words, over here we have chlorine. You know, chlorine hogs electrons. So hydrogen over here is left with the positive. And so anything that is negative is going to be attracted to this side. Down here, we can see that it's equally surrounded by fluorine. There's one, there's another one, and there's 3 of them. They equally surround it, they equally share it, so there's no area that is especially negative, there's no area that's especially positive. Unlike this where you have the negative area and you have the positive area. Atoms that share electrons equally are nonpolar. That's where the electrons can be found all over the place. Not just in one, not hogged by one, but all over the place. How do polar particles dissolve in water? Well, first things that happens is the water molecule surrounds the substances. The example I gave in class, think of the ants that just surround a little piece of watermelon at that picnic. They're crawling all over it. And then bit by bit, they take a little chunk and they pull that watermelon apart. So water molecules, which had their negative side, is attracted to the positive side in the sugar in this example, and they just pull it apart. It gets attracted. So the particles spread out to form a homogeneous solution where it's evenly mixed throughout. It takes time for that to happen. It just doesn't happen instantaneously. So here's the same thing where water is pulling apart the sugar molecule, and sugar is just mildly polar. It's not terribly polar. Notice how it has to be able to get to the edges before it can pull it apart. And that's why the surface area is important. If you want to increase the rate of reaction, you increase the surface area of a module. In this case, you... Now let's talk about solutions containing nonpolar compounds. Nonpolar compounds or substances are not attracted to water. Nonpolar solvents will dissolve nonpolar solutes. So what would be an example of that? Well, if you had something that was very oily and you wanted to remove it, well, you might want to think of something that also is very oily. Of course, then you're left with oily hands. So how do you get rid of the oil? You got rid of the major oil, but you've got a little bit of oil all over the place. Well, to the rescue comes soap. How's soap work? Dirt, which often can be polar, and oil, which is definitely nonpolar, can be removed with water if soap is used. Well, how's that work if like dissolves like? Soap is a nice long chain that has a nonpolar hydrocarbon end that is repelled by water, hydrophobic, and a polar end that is attracted to water, hydrophilic, is water-loving. You've got the one end that is attracted to the nonpolar oil, surrounds it completely, and so the ends sticking out are the ones that like water. You stick your hands under the water, and those ends like going with the water, so they stick to the water and they pull along the completely surrounded nonpolar oil, and it gets carried away by the water-loving end with the water. So soap doesn't really work terribly well if you don't have water that eventually rinses it all off. But think about some of the substances you'd like to dissolve sugar into, and we'll talk about it on Monday and go ahead and create a lab. Enjoy!